So we're going to look at friction today. You've got a handout there. Basically what I've done is I've read through this handout and created notes from it. Okay? So if you feel that you maybe need more information or whatever, you don't quite get something, you could read through this. It's not that long, really, right? Okay? But it basically discusses friction. Now, some of this friction stuff I know we talked about in grade 11, and you might even actually remember some of it. Okay, if you choose to, if you want to write these down as notes, that's great. They're in that handout. I'm basically just going to summarize the key points from the handout. Put it that way. If you want to write them down, you can. If you want to print them off Schoology later, that's fine too. Okay, so a little bit of a refresher here about friction. Jari, please, I just don't have the energy for. Friction is a force that resists motion, and it involves objects that are in contact with each other. There has to be contact. Does there have to be motion for there to be friction?
No. Kind of. No, there's static friction.
Static friction, exactly. If I push it on the filing cabinet lightly, it doesn't go anywhere, but there's actually some friction involved, right? So there doesn't necessarily have to be motion, but there has to be, shall we say, an attempt at motion. There has to be a potential for motion. Exactly. If it was a frictionless world, then there would be motion. Right? What I was saying was that if there was no friction, then there would be in that situation there would be motion. Right? There doesn't have to be motion for there to be friction. What I'm saying is if there is zero friction, then there would be motion in that situation.
How do you stop friction with will?
You don't.
Say you hit a wall.
You don't. Okay, so some causes of friction. There's a handout here you can grab, Kyler. Some causes of friction. They believe, now actually there's a bit of a dispute. They're not entirely 100% sure of exactly how friction works. They believe that an object actually deforms a surface and vice versa. So my binder full of lovely notes there is actually making a little sort of indentation in the table. Okay, so it's sort of sitting in a little hollow. There's some dispute over that. Yeah, that's actually true too. So what they're saying is that there's sort of a little hollow here. A plowing force is required to move the object over these deformations. Irregularities interlock and offer resistance to movement. We all know that things are not perfectly smooth. Okay, so like a tabletop might have all these little bumps on it, as do whenever that slides across it, right? So the little sort of bumps sort of interlock. If you think about sandpaper, when you're sanding wood, right, your sandpaper is obviously very rough, has lots of humps and bumps, and it smooths off the wood. It actually removes part of the wood, right? And that's where you get the heat too. So, Jordan's right that there's some situations where the objects can get so close to one another that there's actually a molecular attraction between them. It's kind of if they get so smooth that they can get that close to each other, then it's actually increased friction. So friction's not that well understood at a sort of a basic. Hey? Like think about glass on glass, right? Right? That would be. Yeah, and I think a lot of that too is also the vacuum that's created too, right? And has to do with air pressure as well. So there's lots of little sort of variables at that sort of basic level kind of thing. Okay, so starting friction is the maximum frictional force between stationary objects. The maximum frictional force is starting friction, sometimes referred to as static friction. And the complement to that is sliding friction.
These are all on.
They will be. Kinetic friction is the other one, right? Sliding friction, the frictional force between objects that are sliding with respect to each other. Now, rolling friction, which is what we're sort of much more familiar with, is actually a form of static friction. I went to an in-service once, and there was a big discussion about this, that the rolling friction, it's only the small part of the wheel that's in contact with the ground that the friction force is on, and that part of the wheel is actually static. It's not actually moving. Okay, the wheel moves around, but that part of the wheel that touches the ground doesn't actually slide. So it's sort of a variation between static friction, although obviously rolling friction is a little bit different. There's also friction between the axle and the bearings and whatnot as well. So basically, we're just going to ignore rolling friction. Some properties of friction. Friction always acts parallel to the surfaces that are in contact, and always in the direction opposite to the motion or to the force trying to produce the motion, right? It's always opposite the motion. And it's always parallel. Friction depends upon the nature of the materials in contact and how smooth they are. That's the only thing the friction depends upon. The nature of the materials, contact, and how smooth their surfaces are. And as I pointed out earlier, there is a point where things can be too smooth and it actually increases friction. Let me get to that. Sliding friction is less than or equal to starting friction. So once you get an object moving, the friction generally decreases. Not all the time. Don't ask me for an example, I don't know. But it can occur. Sliding friction is less than or equal to starting friction. Friction is practically independent of the area of contact. It doesn't matter the surface area. Yes.
If you had a friction and applied force, the friction and applied force is the same, it wouldn't move.
Correct. If it was already not moving. Friction is practically independent of the area of contact. Now, if you think about this, think about it like a textbook. Okay? A textbook sitting flat on a table, or a textbook sitting on its end, sitting upright. Okay? So it's either sitting flat like so, or it's sitting upright like this. The amount of friction is the same, as long as you assume that the space of the book and the spine of the book are the same material, right? There's no more friction here than there is here. So same amount of friction, okay? The area has nothing to do with it, okay? The weight force is what matters. How heavy the book is. What's the force of gravity on the book? And it's the same whether it's like that or whether it's like that, right? So the common misconception, the area of contact matters. Practically independent. Again, I'm sure the Mythbusters could probably come up with something.
Just what they did yesterday.
What did they do yesterday? Starting or sliding friction is directly proportional to the force pressing the two surfaces together, and that is generally related to the weight force. Do you remember what the coefficient of sliding friction is? Anybody remember what the Greek letter for
U? It's the mu.
mu? Greek letter mu. Anybody going to Greece in a few weeks?
That's why.
Yeah? So the coefficient of sliding friction is, where is it here? Mu equals FF over Fn. Now make sure you get in the right order. It's FF over Fn. I've had students before get it upside down, and that causes them a lot of grief.
So, would it always be less than 1?
It is generally less than 1, Jordan. More often than not, it is less than 1. Yes. Okay, so mu equals FFF over Fn. It's the ratio of the sliding frictional force Fn over the normal force. Okay, now I believe if you go through that handout, you should see this example, so you don't have to write down the answer. Okay, let's look at example 1. A box weighing 450 newtons is pulled along a level floor at a constant speed. Now, when you see the words constant speed, that's a good thing. Okay, what does that mean? It means, Jordan, you guys need to listen here. It means that the net force is 0, which is a good thing. Makes it a lot easier. Buy a rope that makes an angle of 30 degrees with the floor as shown. If the force on the rope is 260 newtons, find the horizontal component, find the normal force, and find the coefficient of sliding friction. So the first thing to find is this value right here, horizontal component. Do you remember from grade 11 how to do that? Okay, that FH is adjacent to the 30, so it's going to be cosine, right? So yeah, it's going to be FH is equal to FA cos theta, 260 cos 30. So of that 260 newtons, 225 newtons pulls it actually sideways. So the next step, now we need to find the normal force. Now generally, the normal force is equal to the weight force, right? But in this case, we're actually applying, remember we've got a horizontal component and we've got this vertical component. And the vertical component is actually lifting up. So the vertical component and the normal force are acting in the same direction. So this guy here and this guy here are actually, I can't move it. If I was in Smart Notebook, I could. But if I move it up there, right, then those two together have to equal the weight force, right? So what the vertical component is doing is it's helping out the normal force, which reduces the value of the normal force. The normal force is then the difference between the downward force of the block's weight and the vertical component of the force of the rope. So we need to find FV, and we need to subtract it from the weight force to find the normal force. You can imagine that there's some point, some value that you can be pulling up at an angle that actually lifts the book up enough that it actually isn't in contact anymore, right? Reduces friction down to zero.
Okay, but if you have it, you said like the area is on one side, it's like similar friction. You have it on the corner.
Yeah.
Is that the same?
Yeah. It's still the same weight force, right?
Okay, but if you're dragging it, it's still
Yeah, same amount of friction. Because all the weight is concentrated in there. It's like, got to do with pressure too, right? Yeah. Okay, so what do we need to do here? Oh, I need to finish that, sorry. Since it's moving at a constant speed, the friction force equal to the horizontal component. You guys probably had that figured out already. Here, this goes with this. So I need to find the weight force, or sorry, the vertical component. That's what this is right here. This is the vertical component. FA sine theta is the vertical component, which is 260 sine 30. The weight force is 450, which has reduced the normal force down to 320 newtons. When you lift something, imagine you're sliding like a piano or a heavy box or some other, if you can somehow lift it a little bit, that actually reduces the friction, right? How come? Because you're applying a vertical component. So we've now got our horizontal component, which is equivalent to our friction force, 225. We now have our normal force. I think part C was to find the frictional coefficient. Mu equals FF over Fn, right? So we've got 225 over 320, and you get a mu value of about 0.703. And as Jordan pointed out earlier, generally the mu values tend to be less than 1. In some very rough instances, the frictional coefficient might be more, but most of the time it's less than 1.
If you just left it as mu instead of little,
I probably won't notice the difference. Yeah. It's just a U with, like, instead of going like that, you just go up like that, and then that's all you do. All right. Do you have example number 2? Do you have the picture? No? No picture? Okay. So we've got a wooden block. It weighs 130 newtons. It rests on an inclined plane like this. The coefficient of sliding friction is 0.62. Find the angle of the inclined plane at which the block will slide down the plane at a constant speed once it has started moving. So what we're solving for is the theta, right? Keeping in mind that dot theta is equal to dot theta, and this is also FD right there, right? So the question is, at what angle does the force down the plane equal the friction force? Because when these two are equal to each other, then the net force is 0, and therefore the acceleration is 0. And it moves at a constant speed. Now you have to get it going first of all, right? So you'd have to raise it to some point, get it accelerating, and then drop it down to that angle. And then it should move at a constant speed.
How do we actually use them? Is that possible?
Yeah,
Like down or around?
yeah, because the down force and the friction force would be exactly the same, right? Okay. We could probably, well, I know we can figure it out. In fact, yeah, we can do that. When we do the frictional coefficient lab, we'll do it. The point at which the block begins to slide is when the force along the inclined plane FD is balanced out by the force of friction. In other words, FD has to equal FF. Now remember, where are we headed? Mu equals FF over Fn, right? That's where we're headed, kind of thing, right? We're trying to find the angle,
Yeah.
aren't we? Oh.
And,
Think there's going to be a tan involved?
well, we could do maybe it was 10. No,
Well, remember, I'm guessing this picture's going to come up right away, but remember we've got this triangle here, right? And we've got that angle there, and this is FD, and this is, but what's this FD equal to? Harry, you need to watch. The FD is equal to FF. Oh, but hey, what's FF over Fn? What's opposite FF over adjacent Fn? There's the picture there that I just drew. The tan of theta is equal to FD or FF. The tan of theta right there is equal to FD or FF over Fn. And guess what? What's FF over Fn? It's equal to mu. All you got to do is take the inverse tan of the coefficient of friction. Yeah, there's nothing to it. So when we do the frictional coefficient lab, what's today, Wednesday? Did you say you're away Friday, Quinn? Or tomorrow? Anybody away Friday? Okay, well, we'll probably try and do the frictional coefficient lab on Friday. Okay, where we actually find the coefficient of friction between wood and wood. And we'll do this, and we'll see if we come up with the angle that the block should actually slide down the ramp at a constant speed. Probably Friday. So we'll figure out the frictional coefficient, then we'll get the angle just right, give it a little push, and then it should move at a constant speed. I've never done that before. We'll try it and see if it works. In other words, the block will slide at a constant speed whether the angle of the incline is 31.8, no matter what the block weighs. Did the weight of the block matter at all here? No. Interestingly enough, the weight of the block doesn't matter.
Why?
Do you see any weight, any mass in here?
No, but why does it matter?
Well, because the greater the mass, the greater the Fn, right? But remember, Fd is equal to mg sine theta, right? This is mg cos theta. And so when you go FF over Fn, you've got mg sine theta. The m's and the g's cancel. Oh, by the way, trig identities, what's sine theta over cos theta? Sine theta over cos theta. Tan.
I don't understand that, how the weight is not.
I'll go through that again. I've already told you that the friction, whoa, writing coming back on me. I've told you that in this triangle, this is FD or FF, right? FD is equal to mg sine theta, which means that FF is equal to mg sine theta. And Fn we know is mg cos theta. And so if I go mu equals FF over Fn, that's going to be mg sine theta all over mg cos theta. The m's and the g's cancel, and you get the mu is equal to the sine of theta over the cos of theta. And sine over cos, trig identities, tan theta.
The thing I understand though, like if you have a mass of 1 pound,
Mm-hmm.
and you have like a 31.8
Yeah, degrees.
degrees, and you just slide down, there's no friction there either.
Yeah, there has to be some friction.
No, but like, I don't see where, how much, can you find out how much friction is Actually, it's not one.
It would be mg sine theta. The mass, your 1 kilogram times 9.8 times the sine of the angle.
That's how it works. Oh, yeah.
You're the only one that had an issue with it, Clint.
No,
He didn't.
he's definitely good.
Oh, okay.
No, I asked someone the weight.
Yeah, but that's really like the weight. And how come the weight doesn't matter at all? Because like you have a 1 pound, it's just positive.
Because the mass cancels out. The mass on the top is the FF, mg sine theta. The mass on the bottom is your mg cos theta. The masses cancel out. You can multiply by 10 if you want, but guess what? You're going to divide by 10 on the bottom.
It's true. I get you.
The masses cancel out.
That's it.
All right. I'm done talking. There's a few questions there that you guys can work on. I think I put the solutions there as well. Enjoy some lovely friction questions.
This is from this.
You what?